Welcome back to Acids and Bases and Salts. In part 2 of this unit, we're going to be talking about the definition of acids and bases, like what technically makes something an acid or a base, and dissociation reactions and conjugate acid-base pairs. Let's go. So first of all, what defines an acid or a base? In our previous video, we were talking about what physical properties make you know that it's an acid or base, but what does it mean to actually be an acid or a base? So first of all, we got Arrhenius's definition. This is Svante Arrhenius. He came up with a definition about what makes an acid or what makes a base, and he said an acid is something that just produces H plus, in solution. And a base is something that just produces OH minus in solution. So an acid will have an H in its formula that it's going to give away, and a base will have OH minus in its formula that it's going to give away. This is kind of your junior high definition or your IPC definition. It's a very basic, just acids H plus, bases OH minus, that's it, you're done. But not all bases have OH minus in their formula. That definition of acids and bases doesn't really cover all the different possible scenarios. So Bronsted-Lowry, this is actually two different guys, Bronsted and Lowry, who were working separately from each other but came up with the same idea at the same time, said that an acid is something that donates a proton. And remember that a proton is just a hydrogen ion, and a base is something that accepts a proton. So Bronsted and Lowry defined acids and bases based on how they worked with a hydrogen. Are they taking a hydrogen or giving away a hydrogen? Having nothing to do with hydroxide. So the College Board expects you to know Bronsted and Lowry's definition of what is an acid or a base. They expect you to know that it has to do with the proton being lost or gained. And specifically, an acid is one that loses and a base is one that it gains. So a way that I remember it is the word bladdup. Go on, say it. Say it out loud. It's okay. Bladdup. It's really kind of fun. Bladdup. Bladdup stands for Bronsted-Lowry acids donate proton. Bladdup. Go ahead, say it. It's fun. Bladdup. So you're going to have to remember or memorize that what makes an acid is something that donates a proton, donates a hydrogen. What makes a base is something that loses a hydrogen. Now these are not the only two definitions that exist. There are also Lewis acids and bases that the College Board does not expect you to know. And Lewis acids and bases have to do with the gain or loss of electrons. And I'm just kind of writing this off to the side because the College Board does not expect you to know about Lewis acids and bases. But I did want you to know that there is another definition out there. So if an acid donates a proton, according to Bronsted and Lowry, then according to Lewis, an acid will accept an electron. And a base, which accepts a proton, according to Bronsted and Lowry, would donate an electron, according to Lewis. But the Lewis definition is not in the College Board's curriculum, so you do not have to memorize it. All right, next thing we have is conjugate acid-base pairs. And before we get to the actual conjugate acid-base pairs, I want to talk about dissociation reactions or ionization reactions, how an acid or a base will react in water. So, according to Bronsted and Lowry, an acid, which this thing is because you've memorized HCl as a strong acid, will donate a proton. So it's going to give away its hydrogen to water. Now, if HCl gives away its hydrogen to water, it will make water turn into H3O instead of H2O. But a hydrogen ion is a positive ion, so it's H3O+. Well, once that happens, then the acid, HCl, will just be left with Cl. So it'll be H3O+ and Cl-. HF is another acid, so that acid is going to donate a proton, which means that the water is going to turn into H3O+, and then they'll be left over with an F-. These two reactions look very, very similar. The difference is the number of arrows. The double arrow indicates that this is a weak acid. The single arrow indicates that this is a strong acid. So one of these reactions is at equilibrium, it goes back and forth. and the other one is not. It goes forward and it's done. Then we have NH3, and NH3 doesn't appear to have a hydrogen at the front or a hydroxide at the back. So it might help to draw the Lewis structure for NH3. And notice that the nitrogen has a lone pair. The College Board wants you to know that if there is a lone pair on a nitrogen that's kind of surrounded by hydrogen, something like that, that lone pair is a really great place to take a hydrogen, say from water. So a hydrogen from water will be attracted to the N where that lone pair is. So if that's the case, then it will become NH4+. And then if the water donates a hydrogen, then it will be OH-, because that's the only thing left when you take a hydrogen off of water. That means that NH3 in this case is a base, and water in this case is an acid, not a base, because water is the one that's donating the hydrogen instead of NH3. Okay, so now we've got 3 more examples. I want you to try these 3 on your own. Pause the video now, try to write out your reactions, and see if you get the same things I do. Okay, so let's start with HNO3. HNO3 has that extra hydrogen. It's going to donate that hydrogen, so that's going to turn into H3O+, because the water's gaining a hydrogen, and what's left over is NO3-. HNO2, same thing. It's a weak acid, but the dissociation reaction looks exactly the same. And then we got CH3NH2, and that's a little bit stranger. So let me draw out the picture. CH3, which means a C surrounded by 3 H's, and NH2, an N surrounded by 2 H's. And notice that that nitrogen is going to need a lone pair right there. And that lone pair is the key. That lone pair is going to attract a hydrogen from water. So that, on the other side of the reaction, we'll have CH3NH3+, because it's going to take a hydrogen from water. And if you take a hydrogen from water, what's left is OH-. So that means CH3NH2 is a nitrogenous base, a base with nitrogen. So, conjugate acid-base pairs. This is an acid-base pair, and acid-base pair that differ from each other. Let's see if I can get pretty handwriting here. Only by 1 proton, or 1 H+. To 2 substances that transfer a hydrogen between them. So a conjugate acid-base pair is a pair, an acid and a base, that differ from each other by only 1 proton, so they're transferring a proton in between them. The stronger the acid and base, the weaker its conjugate base or acid. The weaker the acid or base, the stronger its conjugate base or acid. And then one more just definition is amphoteric, something that can act as an acid or a base. So it can gain or lose a proton. And we'll look at some examples of that in our dissociation reactions coming up. So first of all, notice that these are the same reactions that we just wrote. The same HCl and H2O makes H3O+ and Cl-. But now we're going to identify the conjugate acid-base pairs. So we have HCl, which is an acid. And so when HCl donates a proton, what it turns into is Cl-. The only difference between HCl and Cl- is the gain or loss of a hydrogen. So Cl- is the conjugate base of HCl. So with the same idea, water and H3O+, this is a conjugate acid-base pair because water and H3O+ only differ from each other by 1 proton. So if water is a base in this case, then H3O+ is its conjugate acid. So the conjugate acid-base pairs that we have here are HCl and Cl-, and H2O and H3O plus. Okay, so then our next one, we had HF. HF is a pair with F minus, because the only difference between them is one proton or one hydrogen. HF in this case acts as an acid, so its conjugate base is F minus. The other acid-base pair is water and H3O plus. In this case, water again acts as a base, so H3O plus would be its conjugate acid. And in the next example we have NH3 is connected to NH4 plus by one proton. And remember we said that NH3 acts as a base this time, so its conjugate acid is NH4 plus. And then we have water and OH minus. So water can gain a proton or lose a proton, which means water is amphoteric. In those top two examples, it gained a proton, and the bottom one, it lost a proton, which means it can do either thing. So in this case, water's acting as an acid because it lost a proton, so the OH minus is its conjugate base. So now we have the examples that you did. I want you to identify the acids and bases and conjugate acids and conjugate bases in these reactions that you already wrote. Go ahead, pause the video now and do it now. Okay, so HNO3 is an acid, and so then its pair, NO3 minus, is a conjugate base. In this case, water acts as a base, so its pair, H3O plus, is its conjugate acid. HNO2 is an acid, so NO2 minus is its conjugate base. Water, in this case, acts as a base, so H3O plus is its conjugate acid. CH3NH2 acts as a base, so its conjugate acid is CH3NH3 plus. And water acts as an acid, so its conjugate base is OH minus. Remember that we said the stronger the acid or base, the weaker its conjugate base or acid. So in this case, we have a strong HNO3. And since HNO3 is very strong as an acid, then this NO3 minus is going to be very weak as a conjugate base. Because strong means it's forcing the reaction to go forward, and weak means it's not forcing the reaction to go the other direction. So this reaction will go quite far forward. However, HNO2, since it is a weak acid, I know that because double arrow, means that its conjugate base is relatively strong. The conjugate base of a weak acid is stronger, and the conjugate base of a strong acid is weaker. So just keep that in mind. Alright, so on the next page, you've got a couple of more examples. I want you to write the reactions and identify the conjugate acids and conjugate bases. Go ahead and do this one now. Okay, so some of these should look really, really familiar to you. We have HNO3 is an acid. Its conjugate base is NO3 minus. H2O is a base. Its conjugate acid is H3O plus. Then we have NaOH. NaOH has nothing to do but just break in half. There is no water for it to react with. So it's essentially it ionizes. Now, I can't tell you whether NaOH itself is the acid or the base because it's both. It's doing both of those things. But I can tell you about the conjugate acid and the conjugate base. Notice in our other reactions, the conjugate acid always happened to be the positive one, and the conjugate base always happened to be the negative one, and it happens the same way here. Na plus is the conjugate acid, OH minus is the conjugate base. Then we've got, for the next one, hopefully this also looks familiar. NH3 is the base, so its conjugate acid is NH4 plus. Water is the acid in this case, so its conjugate base is OH minus. Then we have HNO2 in water, makes H3O plus and NO2 minus. HNO2 is the acid, so the conjugate base is NO2 minus. Water in this case is the base, so its conjugate acid is H3O plus. And the last one, similar to the NaOH, it's going to be Ca plus 2 plus 2 OH minus. Again, the positive one, hold on, let me make that prettier. Again, the positive one is the conjugate acid, and the negative one is the conjugate base. So that's just writing out dissociation or ionization reactions. Okay, join me next time with your calculator so we can talk about pH and pOH and concentrations of all of these things.